Now we're moving to an online presentation from Dimitrios ZAROUCHAS. This is a demonstration of how the online structural health monitoring was done using acoustic emission sensors.
I don't know if I need to do some. Now, okay, it's working. Good. So good morning, everyone, and welcome to this presentation that actually covers the work that we have done in work package 2. My name is Dimitrios ZAROUCHAS. I'm an associate professor in aerospace engineering faculty of TU Delft. And together with my colleagues, Dr. Saidifar, Dr. Saleh, and Professor De Freitas, we are going to deliver this presentation today. Perfect, it works. So the aim of the work package 2, and in general, the work that we are doing using the structural health monitoring for this hybrid structure is to developing a management methodology for the in situ, so for real-time monitoring of some adhesively bonded hybrid structures that joints that actually were the structure of interest for this project. As you can see in these slides, most of the partners were involved, and the budget was up to 850K. So I would like to start the presentation by presenting to you, at least for the ones that they are not familiar with structural health monitoring, the different 4 levels that they do exist. So in the first level, level 1, what we are trying to answer is the question if there is damage. So yes or no, this is what we are trying to do. On the second level is also to add the severity of damage. And as we go to the third one, we would like also to identify the type of damage. And of course, the last one, which can conclude the goal of SHM, is that as long as we're talking about the structure, we also need to find the location. That's also very important. So these 4 types, answering if there is damage, the severity, identify the damage. We're talking about a composite structure, so a structure that has many different materials. And the location are the 4 levels that we are trying to achieve here. I guess you have seen these slides several times. We are going to focus on the coupon level for the beginning. And I'll show you why there is a need to go lower behind, so to the bulk material, and also how we can go to the large scale test. Starting with the coupon level test, so the second level from the previous. What you see here in the picture is a double cantilever test that we performed in TU Delft. Where you, in the sketch, of course, you see the different materials, and in the picture below it, also the type of instrumentation that we use, the acoustic emission digital match correlation, to measure also the displacement field. The first result that we obtained from acoustic emission is the following. So together with the load, we can also capture the acoustic emission activity. One good health indicator in this case is the accumulation of acoustic emission energy. And what we see here in this graph, it's actually very interesting, is that we can identify where, when actually in the load spectrum, the damage initiates, and load and displacement, of course, and how it propagates. Okay, so we can see also the severity. And we can say with that one, actually, that we can already identify level 2. So the presence of damage, we find it that, okay, the damage starts to occur at this level, but also the severity, how it propagates till the final failure. If you still remember from the level 3, we also try to have the identification. We're talking about different materials here, and the identification is quite important. What we have seen from the tests from the afterwards, so when we check the failure pattern, we've seen different failure modes, like the adhesive failure, cohesive failure, steel deformation, the CFRP skin failure. So these are the 4, so to speak, damage mechanisms that we identify. In order to be able to find how they evolved during the loading process, we need to build classifiers. This is very important. So as I said in the beginning, from the coupon level, we had to go a level below to the material level, so to speak, to the bulk material. And these are the tests that we have developed in order to acquire acoustic emission signals or classifiers, as they said, as they are called. And depending on the four different damage mechanisms, we develop accordingly the tests in order, as I said, to build our test classifiers. So we have the acoustic emission classifiers or reference patterns, if you wish. Then the next step is to build, as we called in the machine learning, so in the training world, a supervised classifier. And then we train this classifier. And from the moment that we have acoustic emission from the coupon tests, then we can correlate and we can compare the different types of signals, and what we can perform is classification. And this classification results to damage identification, of course, which also fulfills the third level of SHM. So in this graph, you see now the different four levels. I don't know if you can also see the pointer there. Hopefully you do. If not, it's activated in my screen. Hopefully it's activated also for you. If not, I do think that we have the different labels. Great. So what actually you can observe already there is the different damage mechanisms and how they evolved over the life. One conclusion from this test is that actually all of them starts at really at the beginning, so at 4 millimeters of displacements. Besides the last one, there's still deformation that initiates almost double the deformation, something that we, in all honesty, we were expecting as well. Somehow, let's see. Okay, so this is the level 3s. And then, as I told you before, one thing that we need to go is to fulfill the 4 levels of SHM. So we do care about the real structure. So for the real structure, what we did there is that we test. So let's skip this part and go to the most important thing is how the structure, so the structural subcomponent, so to speak, looks like, and the different SHM techniques that we used. We have 2 types, so the non-cracked and the cracked one. If in the cracked one, just to see the difference, there is a crack here that we would like to initiate the damage. And besides acoustic emission, and here on your right, you see the topology of the sensors, of the 5 sensors that we used. Also used a fiber optic sensor to, besides the DAC, of course, to measure also the strain field along the length of the joint. This is the way that we did the test. So these are the loading conditions. All the time we did in a displacement control mode. We did 5 load cycles. So that means that we loaded, unloaded, and reloaded. The reason that we did that was to be able to measure also during this load and unload and reload process the severity of the damage that exists already into the specimen. So some results from the two different components, the cracked one and then non-cracked one. So you see also how the specimens fail. And these are the results that we got from the optical fibers, where you see for the different loads patterns, so we have 5 load patterns, how the strain, because this is the length of the fiber, if you remember from one of the previous slides, and this is where the crack and the damage was, the peak that we observed, and how this has changed with the progression of damage. And also the acoustic emission activity, how the acoustic emission activity changes through the loading and reloading process. As I told you, we decided to install 5 sensors, and these 5 sensors could give us the best, so to speak, overview of the structure. So with 5 sensors, we could record the entire structure. And yeah, this is how you see the activity, the cumulative energy activity per sensor. Once we have that, then we need to go back to try to answer also the 4 levels, as I said, of SHM. So on the left part, you see what we have done already with the training, and now on the red part is about the classification and the location of the damage. And these are the some results that we got, and I would like to share with you today. One thing that you can see is that how the different failure mechanisms involve during the load, unload, and reload process for the non-cracked and crack process. So what we observe for the non-crack, so the left graph, is that the cohesive failure is the dominant one. You see also that it exceeds quite a lot the cumulative. Of course, as you may observe, at the end, everything peaks because everything breaks. So you can imagine that is a rupture failure, and the acoustic emission there records a lot. But up to, let's say, the last, before the last loading till the failure, we see that the dominant mechanism is the cohesive. On the other hand, here we, for the cracked one, we see also that the others 3 play also an important role. With the most one is also for the CFRP, and this is something that we managed to identify. That was about the damage classification, so the 4 levels of SHM. Now I would like to go to a bit different topic, because one of the things that the work package 2 had to do is also to describe the protocol, and I do have a couple of minutes still to say a few words on that. What you see here is the, yeah, perfect. It's there. So for the protocol outline and the deliverable that we have already delivered to the partners, these are the topics that I would like to discuss with you today. So, for instance, if someone wants to implement in situ monitoring technique or structural health monitoring technique, these are the things that we do believe need to take into consideration before deciding on which technique to take. So based on the laboratory tests that we performed for this project, something that I didn't say at the beginning, we have 7 SHM techniques. Nevertheless, we decided that acoustic emission and FPGs, the optical fiber measurements, were selected, let's say, for monitoring the real structure. Due to the following reasons. First of all, for the acoustic emission is that the capability to monitoring continuously, that's very, very important. It is very high sensitive. Sometimes this can be also a downside, but nevertheless, in this case, let's put it as a plus. The high sensitivity to early stage damage, and fulfills all the 4 levels if someone follows an approach that we propose or a similar approach. So the 4 levels of initiation, so if there is damage, the severity, localization, and the type of identification. The FPGs, the condition monitoring, again, it's very high sensitivity, and of course, it's real-time measurements. Now, it's there already. So for the capabilities, just to focus a bit more on the acoustic emission, and what we have observed actually from the tests that we have seen is that we can detect damage at a low level, more or less 30% of the maximum failure. So we believe it's quite early. By using a supervised classifier, I can identify the different types of damage into the joint. Nevertheless, I have to say here that in order to build a supervised classifier, you need to do quite some experimental effort, as you saw. So we need to test each material separately in order to be able to have acoustic emission signals. And this, and if someone follows the supervised classifier, this is the only way to go. The damage severity assessment, it is, we've seen that actually the damage is quite severe, up to the level of 6% of the final failure. And for the damage localization, we implement the linear localization algorithm. I'll show you a bit later how it works. The main let's say disability of acoustic emission is that acoustic emission cannot size the damage. So we cannot say how big the damage it is. Of course, with a combination of FPG or maybe another technique, either on the regime of SHM or NDT, with a synergy, we can also size the damage. Now, the sensor installation guideline. We need to determine the maximum allowable sensor to damage source distance. This is important, and this also stands also for the for how many sensors we would like to put into the structure in order to optimally monitor the part that is need to be monitored. As I said, for instance, for the full structure, we did it with 5 sensors. This is an exercise that someone needs to do for a specific structure. We need to ensure that there will be always a very good coupling between the sensors and the structure. There are some specifics about the connection cables, the preamplifiers. We know from some tests that we have done that they should not be exposed to humidity and seawater. So this needs to be taken into account. Sometimes magnet holders and hopefully the industries that they are working with acoustic emission have developed these magnet holders that will help to keep the sensors into position. And depending on the localization algorithm that you want to do, it's advised that most of the cases that you have a linear arrangement between the sensors. For the data measuring procedure, what we have seen and what we have observed is always that we need to have a plus 6 dB higher than the environmental noises. So we need to measure the environmental noises, and the good practice is to add a 6 dB. The sampling rate, that's also important because this will actually define the amount of data that we will have. And depending on the material that we have, so for instance, for a CFRP, we know that when a CFRP breaks, it emits a signal, a sound that is into the regime of 500 kilohertz. So according to the Nyquist theorem, the sampling rate should be at least 2 times that, so at least 1 megahertz. To be in a safe, let's say, mode, usually we go from 2 megahertz and upwards. For the future extraction, when you are doing real-time monitoring, you need to, you want to visualize results. As, for instance, as I told you about the cumulative energy that you can see it in real time. These are the features that we, at least, we propose that someone needs to have in when it measures. And of course, the strategy, as I said, continuously. That's very important. These are for the localization algorithm that someone can use. It's very straightforward as long as you know the speed that you have measured before, and always the sensors measure the time that a signal has recorded. You can also measure then the position of the source. That's the principle. Going towards the end of my presentation, one thing that it is important is to talk about the maintenance. And the maintenance is very, very crucial, because once we have installed, and that's the principle of SHM technique, is that needs to be there permanently. Nevertheless, we need to go back to the system. We need to check that we can still we can get results in a reliable and reproducible manner. And these are different observations that we propose to the user. I don't want to go through on each one of this, but the main message is that an SHM system also degrades over time. It is a system that degrades, and we need to take care of it. And with that, I would like to conclude my presentation, showing some the deliverables that we have, or the dissemination. So several journal papers that they are mentioned here, and some others that they are in progress, like the last one. And some also conference papers that together with my TU Delft colleagues, but also colleagues from Interreg project have developed the last 3 years. And with that, I would like to thank you for your attention, and of course I would be more than happy to answer any questions.
Thank you very much, Dimitrios. That was great. We have a question via the chat. First signals were measured at 60% of ultimate failure load. This shows that the system measures this failure while the joint integrity is not failing. Is that correct, or?
Yeah, because the failure is in a progression. So the joint hasn't failed, but there is already damage, and that's why we measure. And we say that the 60%, the load of the 60%, the damage is quite severe. But as we've seen from the results, the acoustic emission technique can detect the damage initiation at even earlier load, the 30% that I show you, for approximately 30% for different specimens. So if we have a summary, should be 30%. I don't know if this answered the question.
Yeah, this is online. I think they need to confirm by chat. Do we have more questions, okay, maybe from the floor? Yes, please.
Yes, maybe a question related to the noise levels and the noise threshold, because on board of a ship, we try to minimize the noise, of course, but you have a wide broadband spectrum of background noise from all the machinery running. Do you expect difficulties of applying this technology on board a ship?
The frequencies that I guess that these machines produce are on the audible range. So I guess up to 20 or 40 kilohertz, right?
Yeah.
But of course, there can be some harmonics that they can go to the higher level where acoustic emission is sensitive. But there we can really eliminate them with different ways. First of all, this noise might be periodically, so we see something constant and then we can exclude them, number one. Or it is continuously, so they are going to create what we call a white noise, and then we can also filter it out. The problem would be if something sudden happens. If, for instance, something breaks, a system breaks, that is not related to the structure that we monitor. This will give a high peak, and then we need to identify, because the first reaction will be, okay, something happened with the structure. So the noise that is on in a continuously, so to speak, mode, that there are strategies that we can avoid.
Yeah, by filtering the signals for this. Okay,
No.
thank you.
There's a question Yes, Richard, please go ahead.
Yes, I'm intrigued whether you can say a little bit more around the spacing of your acoustic emission sensors based on the experiments that you've done. What sort of periodicity do you think is practical given your experience?
For this specific sensor, for this specific structure, we measure. So the thing that someone needs to do is to measure the attenuation of a signal. Okay. So how much it attenuates in order, and then in comparison with the threshold to be able to record it. This is a very complex structure. It has different elements, and it's quite complex. What we have seen, Richard, in this case is that every 300 millimeters or 30 centimeters, we need to have a sensor.
Thank you.
Great, thank you. Yes, there's another question here.
Hi. First of all, very interesting results about the possibility how you can monitor the integrity of the whole joint. Now the question is also like, since it's the acoustic emission, it depends also on then the material itself, how the wave propagates through the material. It's also temperature dependent. How can you, do you also have then to calibrate your artificial intelligence, whatever is then detecting that for different cases like Saudi Arabia, the Arctic area, there must be quite a difference. Do you take that also into account on a later stage?
Yeah, well, in this case, no, of course, we didn't do that, but there is quite some research going on different environmental conditions. And then we need to compensate on the capabilities of the acoustic emission and the recording signals to be able to identify the effect of temperature on the propagation. But here is the tricky thing. We want to decouple the effect of the environmental conditions to the structure and to the signals themselves. Because an effect on a structure will affect the signal, but an effect on a signal may not has an effect on the structure. So it is really important when we talk about environmental conditions, also to understand what is the effect on the structure itself. So the decoupling process there is of importance, and it's challenging, I have to say.
Yeah. May I ask one more quick?
Yes, of course.
Where is actually on the ship itself? Where is where are the sensors placed? Is it on the outside? Is it on the inside? Is it within the joint?
No, it should be inside. Exactly, I'm not aware exactly where, but should be inside.
Okay. And what if like one of the sensors gets damaged by one of the crew members moving around and then damaging by accident one sensor? Maybe you have a rat on the ship that likes to eat some cables.
Yeah,
one sensor fails, is the whole system still working?
As I said, with the maintenance, commercial equipment nowadays, they have a self-diagnostic procedures that we can run them every N number of days. So we can check if the sensors work, if everything is installed properly. And yeah, that's a way to do it. So we can check actually the sensors. And how to do it? We send signals. So from the sensors, these PZTs are not only receivers, but they can also send signals. So we can dedicate a program, as I said, every N number of days, that actually we will stop monitoring for a while. And then we will send signals from one sensor to the others to check if, for instance, still the coupling is okay. If, as you said, if not a rat went around and kick a sensor out. So this is a way to do it.
All right. Thank you for the work.
Thank you very much, Dimitrios. That was great.